When I first saw this Neuralink demo, it blew my mind. Here is Nolan Darbaugh. He can't move his fingers, he's paralysed from the neck down, but he's able to play Civ 6 on his computer. Now the Neuralink is a type of brain-computer interface, or a BCI, and BCIs have been around for decades, but Nolan's example was the slickest demo of this technology that I'd seen, until I came across Anne reading this research this week. You see, Nolan uses his Neuralink to control a computer. He focuses on a point in the screen and the mouse moves there. Then he thinks, click, and it clicks. He's navigating, selecting, double-clicking, all with his mind. And don't get me wrong, that's super impressive. It sounds like it's out of science fiction. But speech is on another level. When Anne was 30, she was playing volleyball with some friends and, with absolutely no warning, she suffered a massive brainstem stroke. And after this, she was left completely paralysed. So much so that she even lost her voice. Now imagine what that must feel like. To have all of these thoughts and feelings and emotions, but not having a voice, not being able to communicate it with the outside world. Well, unfortunately, this is the reality for a lot of people. People like Anne, or people with ALS, or advanced MS or Parkinson's. For these people, BMIs offer hope, and that's why research in this area is so important. And now, thanks to a team of researchers at UC Berkeley and UCSF, Anne has become the latest champion of hope for BMIs.
You love me there, and
Anne regained the ability to speak. She's speaking full sentences directly from her brain signals in near real time. She's not looking at the screen and selecting letters one at a time, as if she was controlling a mouse like in Neuralink's demo. She's speaking directly into her mind's eye, and the computer can understand what she wants to say. For speech, your brain isn't sending one command at a time. It's generating a stream of tightly coordinated signals to dozens of muscles, your lips, your tongue, your jaw, your throat, for every single word that you say. So when you want to say a sentence, your brain has to do this over and over again. It's like there is a complex orchestra of signals going off in your brain, where every word that you say plays a different note on a different instrument. So this is a really complex problem. For a machine to be able to turn brain activity into sentences, it needs to be able to differentiate each note that's being played by each instrument in this orchestra, and it needs to do this all at once. And that leads to a bigger question. How does a thought become a signal that we can measure? Well, let's zoom in. Your brain is made up of billions of interconnected special cells called neurons. And they're shaped a little bit like trees. They have branches on one end, a long trunk through the middle, called an axon, and then a root-like structure on the far side that connects it to other neurons. Most of the time a neuron is just sitting there. It's using its branches to listen, checking what the vibe is in the neighborhood. But when enough of its neighbors start firing electrical pulses, the neuron gets excited. Its voltage reaches a certain threshold, and then it sends a quick pulse of electricity, almost like a party invite, down its axon and out to all of the neurons it's connected to. Once it sends this electrical message, it resets, it calms down, and then it goes back to listening. And in your brain's motor cortex, this is happening across thousands and thousands of neurons all at once, especially when you imagine moving or speaking. So in your motor cortex, there are thousands of tiny electrical spikes that are firing in patterns all the time. And all of these spikes together create a shifting electronic field. Now, it's not a very strong field. You don't get electrocuted when you touch your head, but it's strong enough to be detected by sensitive electrodes on the brain's surface. So how does a machine read her thoughts and turn this into speech? Well, let's break it down. So the surgeon places a thin strip of electrodes on the surface of her brain, specifically on her motor cortex, and specifically on the part of her motor cortex that controls her jaw and mouth muscles. The difference here in other setups are, for Nolan's Neuralink or the fairly popular Utah array, these are other BMI devices, they have electrodes that get implanted inside the brain tissue, so they need a much more invasive surgery. But Anne's device, it sits on the surface of the brain. When Anne tries to speak, her physical voice, her mouth may not move, but the neurons in her motor cortex, they still fire as if she was physically speaking. So as these different neurons fire for each word that she speaks, the electronic field in her brain also changes, and the electrodes in her ECoG device, they can detect this change and they convert it to data, and that data is then sent to a computer. Now if you're interested in AI, it starts getting juicy. This computer that receives the data runs an AI algorithm, and that algorithm was specifically trained to understand what she's trying to say based on the different patterns it sees in this data. This AI algorithm is actually very similar to the AI used in voice-to-text technology on your phone. Obviously, Anne's not speaking into a phone, so the model doesn't use her voice as audio input. It uses the data that's coming from the electric field in her brain, and then it turns that information to text. So it's like mind to text instead of voice to text, but it's very similar under the hood. And because everyone's brain is different, Anne's AI had to be personalized just for her, for the way she speaks. If I had that exact same device with that exact same model running in my motor cortex right now, it wouldn't work at all. Especially not with my beautiful Irish accent. But anyways, once they have her thoughts converted into text, they use another AI model to turn this text then into speech. So it goes thoughts to text and then text to speech. But her model, it doesn't just sound like a robot voice, maybe like we might remember Stephen Hawking used to speak. They used a clone of Anne's own voice based on old recordings of her speaking from before her stroke, similar to what 11 Labs do. And so she didn't just regain the ability to speak, she got her own personal voice back. Now that's a pretty sophisticated system, mind to text, text to speech. But the team at UCSF and UC Berkeley, they were able to get all of the processing, all of the compute load to process that data done in under a second. So now Anne can have real-time conversations again like she would have used to before her stroke. Now I can tell you, as someone who works in the AI industry, it would have taken some absolutely wild engineering and a ton of training data to be able to get 1 second inference on a setup like this. That's what takes this demo up to the next level of BMI. It's the most impressive technology demonstration I've seen yet. But that doesn't take anything away from Neuralink. They're moving fast too. On April 2nd, 2025, they announced global applications are now open for people with quadriplegia. And other teams around the world are moving fast too. We're entering a new era for brain-machine interfaces. And while the idea of machines that can read our thoughts might seem scary, and justifiably so, this area of precision medicine is a beacon of hope for so many people with severe disabilities out there. Nolan is a pioneer. Anne is a pioneer. And there are so many other people putting their bodies on the line, working with researchers right now in clinical trials. They're all pioneers too. It seems as though every week we're seeing major breakthroughs in precision medicine. This week it was brain-machine interfaces, but if you like to stay up to date with what's going on in the industry, subscribe to this channel. I've been your host, Gary O'Keefe. Ciao ciao!